We divide phase transitions up into first and second order phase transitions. Let's take a look at what the criteria are for a first order phase transition. The phase transitions that you're familiar with, melting, vaporization, condensation, etc., are first order phase transitions. As an example, let's look at melting, where we take a solid to a liquid. Initially, if the substance is in the solid phase and we begin to input energy, the temperature of the solid will increase as the phonon vibrations increase in amplitude, and therefore the particles have a higher average kinetic energy. At some point, the kinetic energy of those phonon vibrations will overcome the potential energy between particles, and the solid will begin to become a liquid. Remember that the solid and the liquid coexist at a given temperature, which we call the freezing point or the melting point, and so as the solid is becoming liquid, the temperature remains constant. Then, once the entire sample has become a liquid, if we continue to input energy, then the vibrations and rotations, translations in the liquid will increase, and therefore the average kinetic energy of the particles in the liquid will increase, and the temperature will again begin to increase. However, if we look at the volume of the sample, initially the solid occupies a small volume. As we increase the amount of energy and the phonon vibrations increase in amplitude, the volume of the solid will increase slightly, although not very much. As we begin to form the liquid, the particles move further away from one another, and so the volume continues to increase in a continuous fashion and at a faster rate. Once the sample has become liquid, the particles stay sort of the same distance from each other on average, although the volume of the liquid will increase slightly with the increasing amount of energy in the sample. So, as a function of time, the temperature is a discontinuous function and the volume is a continuous function. If we then look at how the volume changes as we change the temperature, you'll notice that there is an increase in volume as the temperature increases. So as the temperature increases, a small increase in volume of the solid. When we get to the melting point, the temperature remains fixed at the freezing point, but the volume continues to increase. This results in a jump in the volume between the solid and the liquid, and thus a discontinuity in the volume as a function of temperature. It is this discontinuity that defines a first-order phase transition. Notice that the volume is equal to the first derivative of the Gibbs free energy with respect to pressure at constant temperature. If we were to graph the entropy increase as we melt the solid, we would see a similar thing. The temperature again remains constant during the melting process. However, the entropy is going to increase in a continuous fashion. The solid has low entropy. As we increase the amplitude of phonon vibrations, the entropy of the solid will increase slightly with temperature. And then as the solid becomes liquid, the entropy begins to increase at a higher rate because the liquid has more entropy than the solid does. And thus, if we look at the entropy as a function of temperature, we see a similar discontinuity. Notice that the entropy, the opposite of the entropy, is the first derivative of the Gibbs free energy with temperature at constant pressure. And so for the phase transitions for which you are familiar, the first derivative of the Gibbs free energy is discontinuous as a function of temperature. Thus, the criteria for a first-order phase transition is that the first derivative of the Gibbs free energy is discontinuous as a function of temperature. That suggests that a second-order phase transition is one in which the second derivatives of the Gibbs free energy are discontinuous with temperature, and that is in fact the case. We won't be examining any second-order phase transitions in this course, but some which you may encounter are glass transitions, and these happen particularly in polymer samples which form glasses.